Okay, so Mini-Mod 20 is talking about systems of equations. And systems of equations are when you have at least two equations that form lines, linear equations, and you're using them together on the same graph. Instead of just drawing one line on a graph, you will draw two lines on the graph, and the goal of this is to find out where these two lines cross. And when you find that spot where they cross, you have found the solution to the system. Now, in higher math, you can have more than two equations, and you have to find where maybe three lines intersect or something. But for all of our things that we're going to do, we're just going to deal with two equations, basically two lines on a graph, and we're going to find out what is that common point for them. Where do they intersect? And that spot, the name of that spot, whatever the coordinates are for it, is the solution to the system, meaning that set of coordinates, x and y, if you use those numbers in both of the equations that you're given, they work mathematically. They give us true statements. So, solving systems of equations, we're going to learn three ways to do exactly the same thing. Three ways to find that one single spot where the two lines intersect. Now, one way to do it is called graphing, and that's going to be section 20.2. And then my next video, I'll show you substitution, which is 20.3. And then 20.4 is elimination, also known as, and some people, and I don't even know in your book or, when other people talk, they might call it the addition method. They're both correct. You'll see why. Both words make complete sense, so it really doesn't matter which thing you call it. So I'm going to make 3 videos for you, but I wanted you to understand that all 3 methods are accomplishing exactly the same thing. This one will do it with graphing so we can visually see that common point on the graph, but you can find that common point, that set of coordinates, by doing a little bit of math here or doing a little bit of math here and not even have to draw it on the graph. You can still find out where that spot is. So we're going to do 3 different methods, and you'll find later on in section 20.5, when they give us some application problems, that you can use any of these methods to find the answer, and just based on the problem, you decide which one you're most comfortable with, because you'll get the same answer no matter which method you use. So, excuse me, you have 3 ways to reach the same answer. The goal is to find the one set of coordinates, what we also call ordered pairs, that the 2 equations have in common with each other. The one set that works for both equations in the system. So we'll start with graphing. Graphing is, we've been doing that in the sections before this. When you had a linear equation like y equals 2x plus 7, and you had to find at least 2 ordered pairs so that you could draw a line. Well, now you have 2 equations, so you're going to start with each equation separately, and you're going to draw the line, but you're going to put the lines on the same graph. So find 2 ordered pairs for each equation. Draw both lines on the graph. Where do they cross? What's their intersection? Name the spot, the address, the x and y coordinates. That's the solution. This is the answer we're looking for. This is the solution. And there's a way for you to know if you're correct. I know your homework checks it for you and tells you if you're right or wrong, but the quizzes don't and the test doesn't. So it's nice for you to have the confidence to know whether you're correct or not. And there's a way to check your answer. Check your answer by plugging in the value you came up with here. Plug in that x and y into both equations separately. Put it in one equation for both x and y and see if it gives you a true statement. Does it end up saying 5 equals 5 or -2 equals -2? Then great, you know, it's correct. But if in either equation it gives you something weird like 2 is equal to 7, well, that is never true. 2 only equals 2. 7 only equals 7. So if in either equations it gives you a weird statement when you plug those numbers in, then you know that you must have made a mistake and that that is not the solution to the system, and you need to go back and check yourself, see what's going on. So let's see how it's done with an actual problem. And I'm going to go through what your workbook had, your notebook. I know not all of you have the notebook, but there were some things that it was asking on there that I want to make sure that those of you who do have the notebook understand, okay? It's the solution to a system is the intersection of the lines. So I told you, you know, where they cross each other on the graph. This spot right here is the intersection of it, and that's the spot that is the solution. So if I had this on a graph, and let's say this was like at 2 and -1, then this 2 and -1 is the solution to both equations. I could plug 2 in for x and -1 in for y, and bam, it should work. All right, so to see if the solution is correct, you plug in the coordinates where the lines had crossed and see if both equations result in true statements. Now, to graph something, I'm just going to review that because you know this already, but because you've just done the homework on it, but I'm going to kind of summarize it again. Number one, find 2 points, basically 2 sets of coordinates for each of the equations. Draw each line on the graph. Locate where they intersected, their intersection. This is the solution. And then check your answer in both equations. All right, now if the lines do intersect, because really sometimes they don't intersect, and I'll tell you that in a minute, but if the lines do intersect, if they do cross, the solution is the set of coordinates for x and y where they did cross. And this is called a consistent equation. It's the good kind. It's the easier kind, okay? Now, if the lines don't cross each other, ever, they must be parallel lines. The only way 2 lines would never cross each other is if they're going exactly in the same direction next to each other somehow. So if they don't cross each other, they have to be parallel. And that means there is no solution. There is no common point for them. And this situation is called inconsistent. These are inconsistent equations because they have nothing in common with each other. An example of this would be like if you had x equals -5. So if x equals -5 on a graph, this is what it would look like because there's no y value in that, right? So and you can have problems that have y values that are still going to work here. I just gave an example. If x is -5, it's going to go through the -5 on the x-axis, and it's a straight up and down line. And if x is 2, it's going to go straight up and down on the x-axis as well. These would be parallel lines. So that would be an example of something that is inconsistent, has no solution. And then next, if the lines are the same line, like if you had 2 equations that suddenly created exactly the same line, one right on top of the other, that means that all the points on the lines are the solutions. Every set is common with them. And this is called a dependent situation. Like in this case, if you graphed these 2 equations, y equals 3x plus 4 and 2y equals 6x plus 8, then you would actually draw exactly the same line. And here's a sketch of each of those. Here's intersection, which is the original one that we talked about that's consistent. It has a crossing point. This spot is the solution. Here is the parallel line situation. It doesn't have to be up and down. You could have parallel lines going this way or this way. It doesn't matter, but they're never going to cross each other, so they're considered inconsistent. And then if it's the same line, I put one on top of the other here, or, you know, it doesn't have to be at a certain angle or anything. It's just, are they exactly the same line? Then it's called dependent. All right, so now let's go see an example of how this works. I have system of equations right here. This is the one that's on the notebook. So we're going to graph this, and you can do it a couple different ways. You know, you can do your little chart that they showed you before, where you can just say, oh, what if x is 0? Solve for y. So if x is 0, that cancels this out, and it says 2y equals 10. And then I can divide by 2 on both sides, and it's going to say y equals 5. So now I know I have one set of coordinates of 0 and 5. If I said, well, wait a minute, what if x is, let's say, 2? I could plug in 2 for x. I just picked numbers at random. I didn't, know, I could have chosen something for y instead if I wanted to. But if I plugged in 2, then this is 6. So 6 plus 2y equals 10. So I'll subtract the 6 from both sides, and I get 2y equals 4. So now I know if I divide by 2, y is 2. So when x was 2, y is 2. And so we can come over to the graph, and we can put that particular line at 0, 5 and 2, 2 on the graph, and we can, and I'm gonna put the phone down a second. I gotta use my ruler. Hang on. But we can draw the line and see where that first equation goes on the graph. So here we go again. See, there it is. I just connected those dots. That's it. I drew with my ruler because I've found that if I just freehand it, sometimes they don't cross right because I'm, not a perfect drawer. Computers are so much better. Okay, so then we go to the second equation of the set that they gave us, and we can do the same thing. Again, you can get y alone if you want to and use the slope-intercept equation form to graph it. I don't care which way you do it. But and for these two, I'm just going to stick with the chart for a minute. If x is 0, let's just plug, I like to use zeros. Math is easy with zeros. If x is 0, then this says negative y equals 5. So to find out what y is, it has a negative in front of it. So let's divide by negative 1 on both sides. So y is equal to negative 5. So that's one set of coordinates we know for this equation. And then what if y is 0? I like to, again, use zeros when I can. I didn't use it up here in this one because if I put 0 in for y, this is going to say 3x equals 10. And 10 can't be divided by 3 evenly. That would have been messy. So that's why I didn't choose to do that up here. But if I put 0 in for y here, that cancels the y out, and it just says x equals 5. And so that means 5 is x. So I'm going to go over it and let's graph 0, negative 5, and 5 and 0. So 0 on the x, negative 5 on the y was one spot, and then 5 on the x and 0 on the y is the other spot. And I'm going to go ahead and put the camera down and connect those dots real quick so we can see how it looks on the graph. And here we go. There it is. I connected those two dots and it drew this line. And lo and behold, right here, this is the intersection. This is the piece de la resistance. This is what we were looking for. This is the solution to the two equations. And the location of this spot looks to me like we're at 4 on the x and negative 1 on the y. This is our x and y values. So what that means now, we can go and check. Okay, we're saying our solution is 4, negative 1. That's our solution, okay? We're assuming that's it. To check our answer, I can bring each of the original equations down and just rewrite them just as you see them. Then for x, I'm going to put in a 4 because that's why I'm saying x is. So this is going to say 3 times 4 plus 2 times negative 1 because that's what I said y was. All right. And then I'm going to do the math, and I'm going to see if this, if this is saying this whole thing equals 10. If both sides have the same answer when I do this math here, then cool, it worked in this equation, but it has to work in both equations. So if it works here, we're going to go check this one also. So this says 12. I'm going to use the order of operations, do my multiplication before I do this addition. So 12, and it says plus 2 times negative 1, which is negative 2. So I'll just say 12 minus 2. Sure enough, this side's 10, and this side didn't have any math needed, so it's true statement. Good news. At least we might be right. We're halfway there. Now come over here and do the same thing. If we have 3 times 4, not 3 times 4, I was looking at that problem. Put in for x, we're going to put our 4, so it's going to say 4, and then minus negative 1, so minus negative 1 equals 5, and when you have the two negatives, they come together to equal this positive here. So this says 5 equals 5. Well, that's as true as 10 equals 10. This is saying 5 is the same as 5. Excellent. It's true. And since both things are true, we can be super confident that we did find the solution to the system.